And we're back. So you may notice I've got something written on the board here that looks like I made a typo from what we were talking about last time. You may recall we've been talking about antiderivatives or indefinite integrals. It looks like I kind of forgot the n at the beginning of this. That's not really the case. The definite integral of a function is a different object, and it turns out talking about it it's a problem way older than calculus, actually. So definite integrals, the big thing I want you to get out of this is to think of them in terms of areas. So it really is kind of a geometric idea. So imagine for a moment we have a function f of x, and we've got its graph defined over some interval along the x-axis. I've got it labeled here as a to b. So the idea here is that the area captured underneath this graph, assuming it's non-negative, we'll talk about what happens if it's negative later, this area, we refer to that as the definite integral of our function. So you'll notice this notation looks pretty familiar. So we've got the funny stretched out s, we've got the dx at the end, f of x is sitting in the middle. We call that an integrand. I can't remember if I used that word before. If you hear me say it, that's what I mean, function inside an integral. And we have these things we refer to as the limits or the bounds of the integral written alongside it. I would read this as the definite integral of f of x as x goes from a to b, or just the integral of f from a to b. So this geometric shaded area is the value of this definite integral. So definite integrals in general are numerical quantities as opposed to indefinite integrals, which we saw last time, which are generally functions that we get back when we sort of undo the act of taking a derivative. So that's the idea. I wanted to take a look at this in the context of a couple of examples here. So shunt this guy off. And let's take a look at the first one. So we wanted to look at the definite integral of this function. So the absolute value of x minus 3. And we're interested in this thing as x is ranging from 1 to 5. So I'll draw a graph of this function. Hopefully you remember the absolute value function looks like V for victory. So I should have sort of that sharp corner, and it turns out it's going to be at the place where this thing would be 0. That's 3. So 1, 2, 3, 4, 5. I know my graph starts down there, and I've got a couple of line segments shooting up like so. So that's 0, that's 1, 3, we got 5 right there. And that's my graph. The definite integral of this thing is going to be the area that I'm catching underneath this graph. So underneath these two line segments I've got here, this guy and then this guy. Conveniently, each of those is a triangle, and hopefully you remember how to calculate the area of a triangle. If not, it's 1/2 times its base length times its height. For each of these, we have a base length of 2, and a height of 2 as well, because if you try plugging 1 back into this thing, 1 minus 3 is -2. The absolute value is positive 2, so shazam. Let me go ahead and put that guy in right there. So this first triangle, 1/2 base times height. Second triangle, 1/2 base times height, same thing. And I work out the arithmetic there. 1/2 times 2 times 2 gives me 2. Another copy of 2. 2 plus 2. Hopefully you're not going to argue with me that 2 plus 2 is in fact 4. So that's one example of this guy in action. So interpreting this definite integral thing using areas of shapes we already know how to calculate areas for. So that's one down. Got a couple to go. This next one could be a little bit trickier to maneuver, and honestly, it looks kind of scary when you first see it. So the integral from 0 to 3, that part's not the scary part. This part is the scary part, because we have that radical, we've got stuff living underneath it. First off, remember, please don't try to break this up into 2 separate square roots. It's not square root of 9 minus square root of x squared. That just doesn't work. Please don't do that. That makes me hurt inside. So it can be a bit trickier to try to figure out what's going on here. You may try popping this thing into your graphing calculator and taking a look. You may need to play around with the axes a bit, because just the standard setup. It's going to look kind of vaguely like a parabola if you look at it. That's actually sort of a trick of the way the graph scales are set up, because it's, the graph screen is wider than it is tall. So anyway, as it turns out, if you draw this graph out, it's going to look something like this. You'll be able to figure out the x and y intercepts pretty easily, because if you plug in x equals 3, you get 0, and then, if you feed in x equals 0, the square root of 9 is in fact 3. So we get something that looks kind of like that. And again, it may look vaguely like a parabola. It's actually not. And it turns out, if you play around with this, you may recognize if I try to graph y equals this function, I have y equals the radical. I do some algebra. If I square both sides of this thing, I get y squared equals 9 minus x squared. And then I can rearrange that again. X squared plus y squared equals 9. Hopefully there are some bells going off in your mind at this point, because that's an equation for a circle centered at the origin, and the square root of this guy is in fact the radius of the circle. So we've actually got a quarter of a circle of radius 3. So if we remember how to calculate the area of the circle, we just divide it by 4 and we're good to go. So for what it's worth, your area formula for a circle is pi times the square of the radius. We just said the radius is 3. So 1/4 times pi times 3 squared. 9 pi over 4. So 2 down, 1 to go. And this is where I wanted to transition. So far, we've been looking at graphs that live completely above the axis. So our function is non-negative in this case. We need to figure out what we're going to do in a scenario where it's in fact dipping beneath the axis. And that's where this next example is going to take us. So this last guy I want to take a look at. So we have 0 to 3 and 1/2 minus 1 dx. So again, the function here, we're dealing with the integrand, if you will, is linear. That's kind of useful for us. This time around, if we draw the graph, it's a linear function, slope of 1/2, y-intercept of -1. So let me draw that guy in right here. So we have -1, 1, 2, 3. And you can check this thing is going to cross the, as you say, my y-intercept is right here, my x-intercept is right there. I'm going to fatten that dot up a bit so it looks like I actually did manage to cross the axis in the right place. And now I got 2 pieces. They're each a triangle, but one of them is sitting underneath the axis, and you might end up trying to figure out exactly how to go about resolving the fact that it's underneath there. The catch is we're generally going to treat area that lives under the axis as negative. I know that feels weird. Negative area isn't supposed to be a thing, but run with it for now. So again, this is a triangle. We've got base length of 2, the height of 1 for that guy. Over here, we've got a base length of 1 and a height of 1/2. Again, you can check that by plugging x equals 3 into this thing. 3 halves minus 1 is in fact 1/2. So this area here, 1/2 times 1 for a base length times 1/2. So that would give me 1/4. But I'm going to have to subtract away this area that lives under the axis. So I have minus 1/2 base times height. Base is 2, the height is 1. So I have 1/4 minus 1. As it turns out, that definite integral would have a negative value. I mean, it makes sense because if you look at this, there's more of the graph sitting underneath the axis than there is above it. So if you're thinking about treating that area underneath as negative, that's kind of the idea. So that's a few examples of how to interpret these definite integrals as areas. You might end up asking yourself at this point, what do I do if my graph doesn't give me a really easy to handle shape? We've seen triangles and circles so far. There's some other shapes that might work out, but a lot of other graphs are going to give us much stranger looking shapes. How do we handle those? That's an excellent question, and as it turns out, wait a second, is that Elvis?